Okay, we're going to talk about our last section of wave types today, and that's going to be our electromagnetic waves. So go ahead and set up your notes. Make sure you have two columns, big ideas on the left, tell me mores on the right. You can pause the video if you need to, and then we'll get started. So electromagnetic waves are waves that can travel through empty space. They do not need a medium to travel through. Lots of different examples of electromagnetic waves. Here, X-rays are examples of electromagnetic waves. This is a radio. Radio waves are examples of electromagnetic waves. Microwaves, gamma rays, and then the visible light spectrum that we see. So it's really important to remember when people talk about electromagnetic waves, it's the same thing as when they're talking about light waves or radiation, all meaning the same thing. So let's look at a little more depth what a light wave or an electromagnetic wave is. So the word electromagnetic includes two things. It includes electro and magnetic, right? So electric and magnetic. And electromagnetic waves are transverse waves that are made up of two fields, an electric field and a magnetic field, that are oscillating and moving together. They actually move kind of like this animation is showing. They move perpendicular to each other. So if one is up and down like this, the other one is perpendicular to it like this. And it's also perpendicular to the direction of the energy itself. So how is this electromagnetic wave formed? Because it's kind of crazy when we're talking about these fields here. So let's look at this slide here. And we're going to just walk through a couple steps on how an electromagnetic field or how electromagnetic wave is formed. And the first thing is to remember that atoms consist of different charged particles. One of those is called an electron, and those have a negative charge. Remember that the flow of electrons is electricity. This is kind of where we're excuse me, going here. So if you remember from chemistry, we talked about how the different layers or levels in an atom are based on different energy levels. And electrons can move from one energy level to another if they're excited by something. So remember that a wave is caused by some sort of disturbance, right? And so we just need a little bit of charge or an excitement to get these electrons to move to the next level. Unfortunately, this is not a stable state for the electron, and so they will fall back down to the other level. Well, something has to happen to that energy, right? And so that energy is actually released as little packets of energy called a photon. And within that photon, we have the electric field, which is that movement of electrons, and the magnetic field, which is produced when the electric field is produced. So they work together. They're linked together. So if an electric field is formed, the magnetic field is formed, and the other way around too. And so as those electrons are excited, these little photons are produced, and that is the electromagnetic wave. You may hear sometimes the photons can act like a wave. They have some properties that are very much like a wave, which is what we're going to focus on. And sometimes they act like individual pieces or particles, and they have behaviors and properties of both. So we're going to mostly focus on their wave-like properties, since that's the unit we're in. So some of the ways electromagnetic waves can be described are by their wave properties. Just like other waves have wave properties, so do electromagnetic waves. One of the things you most often talk about or hear about is the speed of light, and that's the speed at which a photon travels. It's extraordinarily fast. Here, 300,000 kilometers per second, which works out to be 300 million, one more zero, I think, meters per second. If you remember, a speed of sound through air is 343 meters per second. So this is a huge difference. The speed of light is amazingly fast. This is the speed of light through empty space. So as the sun's light is traveling to us from the sun through the vacuum of space, it's traveling this fast. But what you may not have known is that light actually travels at different speeds depending on what it travels through. As the medium gets more dense, light actually travels slower. So in a gas, that'll be the fastest medium. Then as it moves to a liquid, it actually travels quite a bit slower, and a solid even slower. Now, of course, it's still traveling very, 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 very fast, way faster than sound, but it's actually getting slower as you move to a denser medium, which is kind of crazy. You always just think the speed of light's the speed of light, but it does change, just like the speed of sound changes through different mediums. Intensity, this is related to the amount of energy that is involved in the wave, I guess. So as the amount of energy increases, the intensity of the light wave increases. But the most familiar ways that you are going to think about a light wave or an electromagnetic wave is usually described by its wavelength and frequency. So they determine, the wavelength and frequency determine so much about the behavior of the wave that they actually set up a scale or a spectrum for the electromagnetic waves. So we're going to look at that next. So here is just a diagram of the electromagnetic spectrum, and then giving you some perspective on the size and energy involved. So most of you guys have probably heard of all these different types of waves. All of these are electromagnetic waves produced in the same way that we talked about earlier. The difference in them is their wavelength and frequency, which determines their behavior, I guess, and how we see them. So at the low end of the electromagnetic spectrum, we have radio waves. These are the lowest energy waves. They have the longest wavelength and the lowest frequency. So here you can see a comparison of the wavelengths as you move along. And then they give you an even cooler comparison in what they would be in real life. So if we were talking about the wavelength of a radio wave, it's huge. It's really long. It's about the size of a building. And then as you move down, right, here is the size or the wavelength of a gamma ray. So much intensity, so much energy. Its wavelength is only the size of the nucleus of an atom. So the tiniest thing, it's so small it's hard to even imagine. That's how intense gamma rays are. Microwaves are kind of a type of radio wave. This is actually the waves that are used to radiate your food in a microwave oven. Infrared means below red. These are what you would think of as like heat waves, I guess, heat rays. Infrared is can be used to, it's like what powers your remote control. It's an infrared wave that will communicate with your TV from your remote control. Visible light, the visible light spectrum is the only part of the spectrum that we can see. We cannot see anything else on the visible light spectrum. This is our rainbow. So we have red waves, so that's why infrared. Down at the lower end, those are the longest wavelength, lowest frequency waves, visible light waves. Orange, yellow, green, blue, indigo, and violet, the Roy G. Biv, right? So violet would be, or purple is our lowest wavelength, highest frequency color that we can see. So the different colors we see are determined by their wavelength. Ultraviolet waves, UV, that means above violet, so they're smaller wavelength, higher frequency than violet. These are the waves that we get from the sun that give us sunburn. X-rays are high frequency, high energy, low wavelength waves. Enough energy that they can pass through soft tissue, but not enough energy that they can go through bone. So that's why we can get X-ray pictures. So it goes through, bounces off your bone, comes back, and we can create an image from that. Gamma rays are your highest energy, highest intensity, lowest wavelength. These are quite intense waves, as you can see by the size. Some of this just is some extra information here, some temperatures and the frequency of the waves below. So do make sure that you write down this, and you may even want a drawing of the wavelengths here so that you know that the lowest wavelength, longest wavelengths are here, shortest wavelengths here, and that it goes in order of intensity and energy.